Good morning, good day, good afternoon, and good evening to everyone. As just introduced, my name is John Winnis, and I'm the Safety Program Manager at CANSO. I will be the moderator for today's session. On behalf of the Civil Air Navigation Services Organization, I am very pleased to welcome you to today's webinar providing more details on assessing the impact of wind farms on aeronautical radar systems, why it matters, and how wind turbines interact with radar and operational impacts on air traffic surveillance to include some mitigation options and key takeaways. At this time, I would like to introduce everyone to Mr. Yahya Khalid, General Manager ATDI Limited, Middle East. Yahya?
Thanks. Thanks, John. Hello, everyone. All right, let's get started. Share my screen. Thank you, John, for the quick introduction. So let's get started. So the topic of today is the impact of wind farms on radars. This webinar aims to provide a clear, practical understanding of how the rapid expansion of wind energy can affect radar systems and used in aviation. It introduces the key interference mechanisms and their operational impacts, then focuses on how these effects are assessed using established frameworks such as Eurocontrol, the NTIA methodologies most of you are very familiar with. So the goal is to equip participants with a structured approach to evaluating and mitigating radar impacts, enabling the safe and efficient coexistence of wind farms and air traffic surveillance. So just quick words about our company, ATDI. ATDI is a global technology company specializing in radio spectrum management and wireless network engineering solutions. We founded back in 1988. We develop advanced software and services that helps government regulators, defense organizations, and network operators plan and model and manage the use of the radio spectrum and efficiently. And that's including coexistence analysis and impact of new technologies on existing technologies. So for the agenda today, we have so many topics to cover, and we have short time, but we'll try to spend enough time on the technical aspects, focusing on the simulation outcomes and simulation methodologies. So in brief, the agenda is to look into the mechanisms of interference taking place between radars and wind turbines and their impact, their assessment methodologies and software modeling approaches and simulation outcomes. So what sort of outcome you can achieve at the end of the day, what sort of report you can produce to help you make a decision, whether it is safe or unsafe for a specific wind farm or specific wind turbines, going through the coordination process. So why this matters? Whether you guys are a believer or not in global warming, okay, that's a different topic. You can still observe during the current regional conflicts that having a single source of energy is problematic to governments. It's problematic to us as well as civilians. So it is difficult to just rely on a single source of energy. It's good to diversify energy sources. It helps reduce the risk significantly. For example, Saudi Arabia has a vision on the 2030 targeting 50% of the energy mix to produce electricity from sources such as gas, wind, and solar. And there's already big projects underway in both PV and wind turbines. A typical wind turbine can produce something in the order of 2 to 3 megawatts. So it's very attractive, but at the same time, the structure is massive. It can reach 250 meters height. So wind energy is expanding rapidly, with national strategies now targeting tens of gigawatts of new capacity, often in proximity to existing radar systems. This creates technical challenges, obviously, as turbines within radar's line of sight can introduce clutter, false targets. It can produce tracking issues, tracking instability, and even localized coverage loss. These effects were first rigorously quantified through the UK Ministry of Defense, flight trials back in 2005, and also later on in the US Department of Defense. There was a report in 2006 establishing foundation for understanding operational impacts. Since then, standardized assessment frameworks such as the Eurocontrol Guide, the NTIA Guide TR08 454 in 2008 have provided structured methodologies to evaluate and mitigate interference. Today, engineering principles are well established, and with careful case-by-case analysis, wind development and aviation systems can coexist safely and effectively. All right, so let's look at the different types of radars that we normally encounter in the modeling and simulations. So primarily we have the PSR and SSR. These are the two main types of radars used in air traffic surveillance, but also used in the defense sector as well. Primary surveillance radars, or PSRs, works by transmitting radio frequency energy and detecting the echoes reflected back from the aircraft. So this is basically an echo concept. It doesn't require collaboration of the aircraft. It's just using the aircraft as a shield or as a reflector, and the signal bounce back, and then you detect the signal. Because it relies on these reflections, it's sensitive not just to aircraft, but to any objects in the environment that can reflect energy, such as wind turbines. So wind turbines are in the way. They create line of sight issues. They create coverage issues, blockage, diffractions, reflections, and so on. We'll get into this a bit later. The secondary surveillance radar, or SSR, works differently. So instead of relying on reflections, it sends out an interrogation signal at 1030 megahertz, and then a signal at 1030 megahertz. The aircraft respond back to you on 1090. So while the SSR doesn't depend on reflected energy, it can still be affected by the signal if it's obstructed. It can still be affected by the wind turbines, basically, if there is obstruction in the way, and that could cause a signal loss. So the key point is that the PSR and SSR behave differently when it comes to interference. That means they need to be assessed separately, even though they are often located in the same site. But generally, guys, the PSR is a bit more conservative because of the way the echo works. So if you secure the PSR sites, effectively also secure the SSR sites. So we'll look a bit into this a bit later. So these three are the main frequency bands that we normally encounter in this domain. So you have the L band, you have the S band, and the X band. These three bands have different characteristics, and eventually you have to, when you study the impact of wind turbines or radars, you need to look at the frequency of the radar being considered. So if you look at the L band, for example, the L band, which is somewhere in the 1.2 1.4 gigahertz range, that band is primarily for radar, for radio navigations. The good thing about this frequency, it really behaves well in terms of propagations. So this frequency can travel far away and commonly used for long-range radars. We're talking about something in the order of 460 kilometers and sometimes more. So it's massive. And they're used for early alarm systems, early warnings, and flights of very, very far away. So the issue with this frequency, the good thing about it, like I said, is the propagation range used for long range. But the issue with this frequency is the RCS. So the lower the frequency, the lower the RCS, which means you're less likely to detect a small target. If you look at the short range, this is something in the 10 gigs. You'll find this is more relevant to precision radars, tactical, local radars, and these ones are precise, but they suffer from short range, but obviously because of the higher frequency, the RCS of the target is bigger, and that's easier to identify small objects. So you'll find like drones can be detected easily with the X band compared to the L band, and the L band can really detect a target far away, but if it is big enough. So these are the different attributes, and the reason we mentioned this because this is going to impact the RCS of the wind turbine and impact the analysis. So If you want to summarize the impact, the aspects, or the concerns when you bring a wind turbine closer to a radar, these are normally the five concerns that you look at. First is the reflections. So reflections, basically the radar transmitting a power is hitting a target and then coming back to you. So if that signal, the echo coming back to you, is too high compared to the noise, it will cause a rise in the noise. Okay, so we call this method I/N, or interference to noise ratio. Sometimes we call it threshold degradation. So this is the first aspect you need to look at, is the reflection aspect. And the bigger the wind turbine, the more reflections, And when reflections come back to the radar, basically they blind the radar and cause a degradation in performance. Now, the second aspect is the false target. So the false target, you can see I tried to explain it here at the bottom. So here you have a radar antenna pattern pointing to the east, and there is a wind turbine a little bit to the north. So that wind turbine is actually coming from the side, and part of the power from the radar will escape through the side lobes. It will hit the wind turbine and come back. And this is misleading the radar. So the radar will think there's a target in front of it because the radar is rotating. And when the radar is pointing in this direction to the north, he thinks there is a wind turbine, or not wind turbine, I think there's a target, a flight or an aircraft, an obstacle, exactly at that distance, which is equal to the distance from the radar to that wind turbine. So you think there's something here, but actually there's nothing. It's on your left-hand side. And to make this even more misleading, we have rotations, and rotation create Doppler shift, which is basically shifting in the frequency. And that shift in frequency is similar to a moving target. So this is how we detect static, how we compare or distinguish static targets from moving targets. Moving targets exhibit a shift or Doppler shift. So we can detect this as a legit target because it's on the move. So even the radar struggled to deal with this because of the Doppler effect. Now, the third concern is the shadowing. So shadowing is very obvious. So if you're looking in a certain direction, and you can see it's depicted here in the second drawing here. So you can see there's a radar shining the sky, and then there is a massive wind turbine in the way, and effectively will cast a shadow. So basically you are blind behind that wind turbine. You have no visibility. And very often they deploy a number of wind turbines in the same location, and that could cast a shadow, and you might lose coverage or visibility in that part of the sky. And the last point, Doppler, I already mentioned Doppler under the false target because these two are related. The last point is overloading. And overloading is also a concern, but normally it's a concern when the wind turbine is very close. If the wind turbine is very close, it's going to shine really bright, and that strong reflections basically is going to saturate the receiver, and the receiver will struggle detecting signals. And also that could happen at post-processing stage when you have large number of wind turbines in the area with a Doppler shift. With the rotations, is going to create a large number of targets, and that could overwhelm the post-processing aspect of the radar. So this is just a high-level breakthrough of the different aspects that you should consider when you are evaluating the impact of wind turbines on radars. Now let's look really what's happening at the receiver level. And the reason I need to talk about this is because this is considered a detailed analysis. So normally when you want to analyze in details what's happening at the radar level as a result of a wind turbine, you need to look at something we call the I/N, and we need to look at the saturations and so on. So any receiver, any modern receiver these days have something called AGC, which is basically automatic gain control. The idea of the automatic gain control is to deal with the variable signal power. So if you have a strong signal from a nearby aircraft, the signal is strong enough, you can detect it without amplification, okay, or with moderate level of modifications. But if the signal is very far away, if the target is very far away, the signal you receive is very faint, and the receiver has to amplify the signal a bit. So it is dynamic. So this is dynamic gain control. We call it auto gain control. Now the issue with this, I will show you in an ideal case how it works. So if you look here at the first case, we have here a strong signal coming in to the LNA, which is the low noise amplifier. A strong signal comes in and comes out nice and happy, strong. Now a weak signal comes in, it gets amplified and get out of the LNB happy, and the receiver can deal with it and decode it correctly. So basically the LNA is smart. If a signal comes in strong, it will attenuate it. If it's coming weak, it will amplify it. The idea is to keep consistent output. You can see it here. This is a blue signal, and the signal here, the blue sinusoidal signal, you got a strong signal, weak signal, strong, and then average. And you can see the output is consistent, so consistently good. So the idea of the LNB basically is to deal with these changes in the signal dynamically and deal with it. Now, what is the issue with this? The issue with this is that the LNB or LNA is not too smart. If you happen to receive two signals now, wanted plus unwanted, so you got a weak signal coming from the aircraft, and hopefully we amplify it, and then you're getting a strong signal coming from a local wind turbine reflected back. These two arrive together. The LNB or the LNA thinks, oh, signal is good, I don't need to amplify it. Okay, it doesn't distinguish that this is a front end receiver. It doesn't distinguish between the good signal and the bad signal. So the LNB thinks the signal is strong, and then it decide I don't need to amplify much. So you see the bad signal comes out really strong, and the weak signal is attenuated and basically becomes too low to be decoded. So here, what the wind turbine did, actually, it reduced the sensitivity of the receiver, okay, or caused saturation to the receiver. And here you effectively have lost coverage range for your radar. So your radar lost the coverage range, maybe dropped from, let's say, 400 kilometers to maybe 250 or 300 kilometers because of the strong reflections coming in, causing rise of the noise. So this is a very common issue you can analyze. Now the second major analysis you need to do is the I over N. So the I over N, basically the concept is to compare the reflected signal. So here we have a wind turbine, here we have a radar. The radar is transmitting a signal, hitting the wind turbine, and then bouncing back to the wind turbines, so to the radar. So the radar has a certain noise level, and this is the noise of the receiver. In an ideal situation, or in the absence of the wind turbines, there's a certain noise level in the environment, and that noise now is further lifted up by the presence of the interference. So I will explain the concept here and how it works. So normally, guys, in the universe, there is a background noise. You know, there is a constant vibrations in the spectrum. You call it the cosmic microwave background noise. So basically, it is roughly neg 174 dBm in 1 Hz. So the noise is very low in the universe. It's neg 174 dBm in 1 Hz. Now the radar, long-range radars, they need few kilohertz in order to detect a target far away. So normally you have long range and short range, medium range radars. The long range radars are normally narrow bandwidth. They have narrow bandwidth. They don't need too much spectrum or too much bandwidth from the spectrum. So they need less. And the advantage of this is that they accumulate or they see less noise because the opening is narrow, so they don't detect too much noise compared to short-range radars. They normally broadband, and they normally have more bandwidth, which means they can pick up more noise. It has some advantages, have some disadvantages. So here, well, my focus is on the noise level. How do we establish the noise level for the radar, and then how we compare the interference or the echo coming from the wind turbines to the noise level. So that, like I said, the universe have a constant noise. We call it the K, the Boltzmann constant. Now, Boltzmann constant multiplied by the temperature, so it will give you -174 dBm. And the hotter the environment, the hotter the equipment, the more noise you'll pick up. Okay. Now, after this, you have to scale it by the bandwidth of the receiver. So if your radar is at 12 kilohertz, for example, so you need to scale it by this amount. So it become KT plus 10 log the bandwidth. Okay, so your sensitivity will increase from or decrease, in this case, from -174 to -120. Okay, so that's how much noise the radar is seeing in the assigned bandwidth. Here we're making assumptions about the numbers. Now, after this, after the KT, you have the noise figure of the equipment. The radar electronics have internal interference. The internal interference will lift up the noise of the radar further to -117 in this case. Okay, so this is called now the KTBF. This is the noise. So now you see we started with the universe, how much universe has noise. Then we added the receiver bandwidth to the noise because it's picking up more noise now, until we reached the -117 when we introduced the equipment itself, the noise figure. The radar noise figure can be somewhere in the order of 3 dB, maybe to 7 dB, depends on the quality of electronics. After that, for the radar to detect the target, the signal need to be above the noise by signal to noise ratio. That's why here I put sensitivity equal to KTBF plus signal to noise ratio. All right, guys. So basically, this is what a signal should look like in order to receive a target. The signal coming from a target need to be exceeding -115 dBm in this case in order to detect an aircraft or a drone or a target in the sky. Okay. So when we protect the radar from wind turbine, we are actually very conservative. So look what we do. We actually don't look at the sensitivity of the radar. We look at the noise level of the radar. So we make sure no reflections from any wind turbine come in this region here, the next 6 dB region. Okay, and we take the noise level, the KTBF, as a reference. That's why we call it I/N, or noise degradation approach. So we make sure any reflection coming back from any wind turbine is below that that zone, that exclusion zone. Make sure it's below. Okay, so if it goes below, then the impact on the wind on the radar is manageable. And you can see here I have a relationship between threshold degradation, which is how much degradation is happening on the how much hearing capability you are losing. Basically, TD is a threshold degradation. So that the degradation is related to the I/N, and you can see here I have a graph. So a TD of -6, like I said, is the target, is equal to 1 dB degradations. So basically, we are saying we can tolerate interference as soon as the degradation in the radar is less than 1 dB. And some organizations might go beyond this, might go to -9 dB, which is about half a dB degradation, or 0.2 dB degradations. Okay, so this is the approach, and every 1 dB degradation you experience, it's causing more loss to the sensitivity and to the range of the radar itself. So this is what we call the I/N method, and this is the notion behind it. So if the interference coming back is in the green zone here, safe, is considered safe, then we can accept the interference. And again, guys, this is considered detailed analysis. Most of the time, we can deal with the application, incoming application for a new wind turbine or wind farm. We can deal with it in a simple way, and if it fails, then we can go to a more in-depth analysis. And this is fairly automated in a planning tools. So in summary here, if you look at the behavior of the receiver behavior, let's look at how the radar systems process what they receive. So every radar has a noise floor, like we said, which comes from natural thermal noise in the receiver. To avoid false alarms, the detection threshold is set just above this level. Increasing noise floor due to local reflections means reducing the sensitivity of the radar and risking early alarms. You could lose some alarms. To improve this further, radars use something called constant false alarm rate, or CFAR. This means the detection threshold automatically adjusts depending on the local environment, helping maintain a consistent rate of false alarms even when climate changes. Radars can also apply filtering techniques like the MTI and MTD. This compares signals over time or frequency to suppress stationary objects, such as wind turbines, if they are stationary, of course. So things like terrain and buildings are filtered out. They can deal with this easily in software. It's normally post-processing as well. This is where Doppler comes in. So moving targets like aircraft have a Doppler shift and can pass through these filters, which stationary objects are rejected. So finally, the radar can group detections into plots and then into tracks. This tracking process has limited capacity. So too many false or cluttered detections can impact overall performance. So if you have a large number of wind turbines, they're all rotating, and for the computer software processing these imageries, it can get overloaded because it has a certain capacity. So let's look now at the most important part in the simulation, the antenna. So if you have a good antenna modeling, you can have a really good estimate of the interference. And you know, in any communication systems, normally antenna is the most critical element in your transceiver chain. If you have a poor antenna, you have poor performance. If you have good antenna, you have good performance. And the same in the radar. So normally radars are designed to have an elevated beam. Basically, you are trying to monitor the sky. You're not trying to monitor the ground. So here I'm creating a simple antenna pattern. And that antenna pattern is pointing to the sky. You see, pointing towards targets. Normally, you have a positive elevation scanning. Now, the wind turbine is typically on the ground. It's not a flying target, and most of the time is in a negative slopes or negative elevation angles. So what happens is when you have a good antenna pattern in the software can actually evaluate the antenna discrimination in the direction of the wind turbines. So a signal going up to the wind to the drone actually will experience minimum attenuation because it's going through the peak of the antenna. Whereas the antenna pattern, whereas the radiation going from the side of the antenna pattern here, it will experience attenuation at this spot, and the attenuation will be experienced twice: when it's leaving, hitting the target, coming back through the same journey, and then coming through the same spot. So here, this spot is considered attenuated or discriminated compared to the main lobe. Okay, so this is going to be very handy. And when we model this in the software, it's important to load antenna patterns, as they can give you more chance to coexist. If you're going to just assume omni, then it will be impossible to coexist between these two technologies. And that also suggests, guys, if you have a higher elevations, elevations and antenna patterns, then more likely you can coexist. There will be less impact from the wind turbine on the radars. We'll also go into this a bit further in the next few slides. So, guys, this is radar antenna pattern. This is a real one, and this is a military one. I think this is the FBS, the 117. There's two types of radars. There is the classical radar that have a single beam, and then there is the modern radars that have multiple beams. And the modern radars have multiple pencil beams. These pencil beams really immune to these sort of interference issues. So if you look at the top one here, you can see the vertical pattern, and this is the horizontal patterns. And we generated this using software, and you can see here the number of antenna elements that were used, because this is an array antenna, the defense ones, FPS 117, TPS 77, TPS 78, and GM 200. So these radars are all considered smart radars, and they have a number of radiating elements vertically and horizontally, and using this information you can reproduce the antenna patterns. All right, so this antenna pattern need to be generated, and then once you generate it, you can import it, or if you already have it, you can import it into a simulation tool in order to model this effect. This is how the antenna, how the radar radiation beam look like in a 2D space. So you've got 2D space here, vertical, and on the elevation angle on the vertical axis, and then you have the azimuth on the horizontal axis. And this is the energy. The energy is focused in a very specific spot. This is because it's very, very directive. And this is an example of a pencil beam. So it's pointing upwards, and normally you have multiple beams pointing upwards. This is here a quick comparison between classical winter radar on the left-hand side. You can see this is a classical vertical beam. Okay, this is single beam. So the rotating antenna is transmitting this vertical radiation pattern, and you can see it is designed to focus the energy in this direction, like 5 degrees, 6 degrees, 7 degrees above horizon. And it's not designed to monitor very high altitudes just above the radar. So and at the same time, you see at the horizon level, the zero degrees here, it has really strong discrimination. There's a signal loss in this direction. And that makes sense because you don't want to pick up too much clutter from the ground, like trees or mountains and terrain and so on. So it is focused a little bit up. This is a single domain, basically, from interference perspective. This is a single domain. Now, on the right-hand side, you see this is a modern radar, where, especially used in defense, where you have multiple beams. And these beams can turn on and off at a very high speed, basically scanning the sky. The weather radar also operates in a similar fashion, but it is mechanical scanning. So you can see here, guys, we have multiple beams. And when you experience interference on one beam, it doesn't mean the upper beams would suffer the same. Actually, you become more immune and less likely to be impacted by the wind turbines. So you can say the classical antenna, the classical radar antenna, is a single collision domain or single interference domain, whereas the multi-beam has multiple collision domain, and you can evaluate the impact on each beam separately. And by the way, this is a great idea for mitigation. So if you have a classical radar and you're suffering with strong reflections or interference from wind turbines, this is a great way to reduce interference by having like a array or pencil beams. Now, propagations. So we talked about the I over N method. We talked about the saturation method, the interference that happens because of reflections. We also talked about the antennas. The antennas are very relevant in our modeling. Now let's take this a bit further and talk about the environment itself. So very often you find the bulge of the Earth and terrain acting as a natural barrier. So it's important when you do this kind of simulations to have a 3D model or a digital terrain model for the area of interest or for the country you're doing simulation in. So here on the right-hand side, I have Kingdom of Saudi Arabia. So you can see towards the west, the southwest, you have really heavy terrain here around Mecca, Medina, and so on. This is heavy terrain. And these terrains act as a natural barrier. And also, like I said, the bulge of the Earth is going to help a lot, allowing you to deploy wind turbines closer to the radar. So first, let's establish what is a good propagation model for this kind of simulations. First, we use because radars are normally evaluated based on free space loss. So we use here free space loss, which is basically 20 log F plus 20 log D plus 32.4, which is the ITU 5 to 5 recommendations. So you could use free space as your main propagation model, assuming you complement it with visibility rules. So visibility rule, what does it mean? It means I need the software to predict the signal if there's a visibility between the radar and the wind turbine. You can see here at the bottom sketch here, guys, you can see there is an optical line of sight here in the middle. This is we call optical line of sight. So if this optical line of sight is clear of obstruction, so that means the wind turbine is visible, we consider this a free space conditions, or we consider it visible. And if it is visible, then we apply free space loss formula as is. If there is no line of sight, like this case, the top case, you see the optical line of sight is going is above that wind turbine, so there's no visibility. Basically, if you're standing there, you cannot see the wind turbine. And by the way, we cannot see it here. It means we are also considering the K factor. So we are flattening the Earth by a factor of 4/3, flattening the Earth, because this is the behavior of the signal propagating. So we're flattening the Earth a bit, okay? And then we do this visibility analysis. If there's no visibility, then there is no signal. We consider this no signal. We return no signal. Okay, and if there is visibility, then we predict the free space loss. Now, free space loss, we know it's not sufficient, so we add to it a sort of subpath attenuations. And the reason we add this attenuation is because, look at this example here. We know the signal, most of the signal propagates in that Fresnel zone. You see that Fresnel zone here? So this Fresnel zone, if it is not obstructed at all, we consider this free space conditions, but it is partially obstructed. It's partially obstructed, and there's still optical line of sight. Because of this obstruction, you expect to have some losses. So we estimate this losses based on the subpath formula that we have here. We call it the area. So basically, guys, we take combinations of a free space loss, visibility, and also subpath attenuations in order to compute the signal accurately. If you don't have a good propagation engine, then this analysis becomes useless when you do it. So bistatic radars, guys. Now the idea of interference between radars and wind turbine is actually coming from the bistatic formula. So it's a simple link budget. You have a transmitter transmitting a signal, received here, transmitted back, received here, and you can think about it like a bistatic here. That bistatic model. So bistatic radar, basically you have two radars, one transmitting, one receiving. So this is transmitting signal and then reflected back, like this is like a mirror, reflected here, attenuated of course, and then transmitted back to this one and received here. This is the formula here. It relates the power received to the power transmitted going through this transmission chain or channel. So you've got here transmitting power, leaving free space loss, and then hitting this attenuated, and then traveling again free space loss, and then receiving here. Now, this is a bistatic formula, as well known, well understood. We apply the same concept on this case, where to evaluate interference from the radar to the wind turbine back to the radar. So basically, it's a self-interference model in that case. Now let's look at the wind turbine itself, how the wind turbine is modeled. So again, to summarize, so we talked about the radar itself, the antenna pattern. We talked about the interference mechanisms. We talked about the propagation mechanisms, and now the turbine itself. How are we going to model the turbine? So normally turbines is characterized by its height, the hub height, by the diameter of the mast, and also characterized by the diameter of rotation. This is very important, the diameter of rotation here. So wind turbines, guys, are somewhere between 150 or sometimes smaller, up to 250. And what we've seen, a massive one, 250 meters from the ground to the top of the blade. Okay, so this is how you model the wind turbine. The wind turbine need to be reduced to RCS. RCS stands for the radar cross sections. Basically, how much shining it's producing back to the radar. And just to put this in context here, you see, let's compare. If you look at this 747 aircraft, it is in the range of 10 up to 1,000 square meters. So the effective area from the radar perspective for that jet 747 is somewhere between 10 meters and 1,000 square meters. Depends on the orientation, depends on the angle, depends on so many things. And if you look at a bird or a man, let's look at the man. The man is roughly one meter. So a man also receiving a signal, reflect back part of the signal, roughly 1 square meters. Okay, so if you look at the jet now, the rocket, you look at the rocket, it's somewhere in the order of 10,000, or yeah, about 10,000 square meters in size. Now let's look at the wind turbines. So here I have interesting cases. So this is based on measured. So you see this radar, this wind turbine. This wind turbine is about 113 meter. The rotor, okay, it's about 113 meters in diameter, and it's producing roughly 40 dBSM. This is dBSM. 40 dBSM, which is maybe in the order of 10, about 1,000. 40 is about 10,000 square meters. Okay, 10,000 square meters for the 40 dBSM, and you can see it is higher for the S band. All right, that's important. So the same wind turbine have a higher RCS at a higher frequency. So the higher the frequency, the more reflections, the bigger the RCS effect. So this is based on measurements from a study. They've done some measurements for 113 rotor wind turbine, and they found 40 and 48 for L band and S band. Now, in comparison, here I've got here 200 meters. This is bigger one, 200 meters rotor, and you can see the numbers jump from 40 to 44.6, and from 48 to 52.5, and this is in square meters. It's 28 or almost 29,000 square meters and 176,000 square meters. So they are massive in terms of how much footprint they would have on the radar and how much reflections they will produce back. And I left here for you guys this formula in case you want to convert. If you have measurement at a small wind turbine, you want to scale it up on a bigger wind turbine or scale it on a different frequency, you've got this formula here to help you do the scaling. And also, just for the completeness, I included this. This was done by a study, and I left the reference here. This is showing you over time, because there's rotation. The blades are rotating, and as they rotate, you can see the RCS is going up and coming down, going up and coming down. So RCS is actually, guys, function of time because of the rotation, depending on the angle, the pitch, and so on, and the speed. They all impact the RCS value. So in a simulation, you could take a worst case scenario, or you could take average case scenario. This is also an interesting study. I also left the references here. So basically what these guys did, they looked at the velocity aspect. So you've got here industrial, actual full-size industrial wind turbines. So these wind turbines, guys, and you can see here for reference, the sizes 130, 146, and 130 meters. And they're producing 2.3 megawatt, 3 megawatt, 1.8 megawatts. And I can read here Siemens. The first one is Siemens. The second one is Sinovel. And then the third one is Vestas. Okay, these are three different products from different vendors. And here, what they've done in the study, they actually measured the RCS at different velocity. So right in the middle, we have 0 velocity. So the blades are stationary. When the blades are stationary, you can see it's peaking. The RCS is going to the top, and it's somewhere in the order here. For this is S band, by the way. This is S band. And it's going up, the average is going up to 40 dBSM, 40 dBSM. And if you increase the speed, this is the velocity. If you increase the speed, you can see it is reducing. The RCS is reducing. But obviously, you cannot do your modeling based on assumption that there's no wind. So actually, they positioned these wind turbines at the strategic locations where the wind profile is really helping. So you expect there should be some rotations, and the dotted lines are actually the max, the instantaneous or the max. But whereas these ones, these are the average figures. Now comparing the S band to the L band, you see the L band, guys, is lower. You see here the maximum is 40. Here the maximum is 50. So L band, because L band is lower frequency, the RCS is naturally lower. Okay, so don't assume your wind turbine have a constant RCS. RCS is variable based on the frequency you are using. Now let's look quickly at the. We already evaluated this, so we'll touch on this very quickly. This is the classical radar. So we have a single domain, a single collision domain, a single interference domain. So you have this common antenna radiation pattern. This is used in ATC, air traffic controllers, and so on. So like I said before, guys, we can actually compute based on the Earth curvature, the geometry, the antenna height, the radiation pattern, the RCS, the wind turbines. All of these guys you're looking at, they're coming into the computations, they come into play when we estimate how much interference is received by the radar. The software has to have the antenna pattern, have to have the propagation formula, have to have the terrain, the Earth curvature, the geometry, the antenna heights. All this information will go into the software to estimate the power received, and then compare the power received to the noise and decide if it is causing interference or not. So this is the first aspect, I over N. Now, the second aspect is the shadowing. So we spoke about shadowing before. The shadowing is very clear, guys, very obvious. So we can it's like the radar is shining the sky. Okay, the radar is shining the sky, and then this wind turbine is in the way, casting a shadow. Now, if you have aircraft behind the shadow, it doesn't mean you will not really. It's not visible. It's not. There's no reflections coming back. There is reflections coming back, because signal can operate beyond line of sight. Everybody agree on that. So if there's a target here, that target will reflect some signal back to the wind turbine, and it will be diffracted or whatever back to the radar. But don't forget, the wind turbine itself is shining stronger than you. So when you have a signal leaving the radar hitting the wind turbine, it will come back, and then that weak signal coming from here is negligible compared to the echo coming from that wind turbine. So basically, this area become useless. It's because of the shadow. So a turbine in the line of sight attenuates the signal on both trips. So when it's coming from the radar to the target back to the radars. All right. So and by the way, the further away this wind turbine, the further away, the less likely it will cause shadowing, because like we said before, the radar is trying to monitor the skies, not the grounds. So the further away the wind turbine from the radar, the more you have separation distance, the less likely you will suffer from shadowing. Clearance angle. So that's why when we do shadowing, we look at the clearance analysis. There's something called clearance analysis. We do I over N analysis and clearance analysis. And clearance analysis, guys, is very simple. Basically, we need to have the elevation or the scanning angle of the radar, and we need to know the beam widths, the 3 dB beam widths of the antenna, and we compute. So scanning angle minus the 3 dB beam widths divided by 2. Okay, it will give us this clearance angle. So that green area, if there's obstacle under in the green area, if there's obstacle under that line, it is considered not causing shadowing, not causing obstruction, because it's below the main lobe. Okay, it doesn't cause shadowing, but it doesn't mean it doesn't cause interference to noise ratio problems, I over N problems. So we normally have to do both analysis, clearance and the I over N. So the further you can see, if I push the radar or the wind turbine, if I push it away here, it's easier. That give you more height, give you more freedom to install higher or bigger wind turbines the further away they are. And this can be decided and judged quickly using software. So guys, Doppler, just to complete this topic, so in a primary surveillance radar's environments, rotating wind turbines blades introduce unique challenge by impacting Doppler shifts to the reflected radar signal, effectively spreading the return across harmonics of the blade rotating rate, with modern multi-megawatt turbines reaching blade tip speed in the range of 50 to 80 meters per second. These Doppler components often exceed the typical moving target indicator thresholds. Okay, so they can cause a problem. This is, guys, this is a very interesting image. This is showing you that the Doppler shift, how much Doppler shift we have because of the rotation of the blades. This is just a time domain here, and here is the frequency shifting domains. So you can see, guys, a wind turbine operating causing 750 Hertz Doppler, it will give you a fake target around 135 kilometers per hour. If your radar is operating in the 3 gigahertz band. If your radar operating in 1 gigahertz band, you see a target operating at speed 405 kilometers. So this can create a false target, and normally you can analyze this easily using software by checking the power received from the radar. Okay, so in terms of the impact, operational impact, so we have detection degradation. So the radar front end and sensitivity and range start to degrade. Okay, so we will have false plots and tracks on the screen. We have tracking instability. We have coverage gaps at certain altitudes, certain sectors, and the controller, the software aspects of the radar can get overloaded. Okay, so these are the impacts on the radar. So this is the European approach. The European approach, they have a very methodological approach. Basically, they reject any radar at 500 meters, and they require basic analysis if the wind turbine is within 15 kilometers and within line of sight, and they require detailed analysis. And if it is beyond 15 kilometers and less than the range of the radar, and still within line of sight, they consider this as a simple case. You do simple analysis. So you see here, this is simulation coming from software. We have a radar in the middle, and we have these colors. These colors indicating the 4 zones that we're talking about. This is the American approach. So the American approach, normally they have a simplified version. They look first at the Earth curvature. So they assume Earth is flat, no terrain, nothing, and then they do the quick filtering criteria. They establish if the wind turbine is within line of sight or not. If it is not within line of sight, then accept. If it's within line of sight, then they push for further analysis like shadowing, terrain, I/N analysis, and so on. So this is what we propose as a methodology, which is in alignment with both the Europeans and with the Americans. So if there is any wind turbine within 500 meters, to reject it without checking line of sight or anything. If you have a radar, if the wind turbine is not within, or if it's beyond the maximum range, if the wind turbine is beyond the maximum range of the radar, just accept it. Just accept it. Don't bother. And if it is within the range of the radar and within line of and it's not within line of sight, also accept it. So this is the golden rule. If the wind turbine is not within the line of sight, just accept it. And that line of sight is what I defined for you guys: the visibility, taking into account the Earth curvature, taking into account the terrain, the heights of the wind turbine, the height of the radars, and so on. So if it is within line of sight and within the range of the radar, then here we do detailed analysis. And really we focus on reflections and shadowings. Okay, so shadowings and reflections are very critical. And if you fulfill the reflections problem, like I/N, you really also fulfill the Doppler problems and other problems. And this is the sort of simulation outcome that we produce. So we can do analysis for every radar against every wind turbine. We can establish the I/N, which is interference to noise ratio that we spoke about. We can establish if it is seen or not seen, so visible or not visible, and we can get the angle, the angle from the radar to the wind turbine, the elevation angle. It's normally negative. So this elevation angle we can judge based on this angle as well quickly if the wind turbine is fulfilling these 2 criteria, the I/N and the shadowing. So guys, in summary, the line of sight is the main criteria used to accept quickly. If something is not within line of sight, you accept. If it is within line of sight, then we have to do analysis. And the analysis which is recommended is the I/N with a target of -6 to -9 dB. -6 is considered adequate and conservative, and the -9 is even more conservative. So before I finish this, guys, I'm just going to do for you a live demo just to show you quickly. This is the tool, and this is the terrain that we are using. So you can see the terrain here in the background. So and the Earth curvature is considered in this modeling. You can see it clearly here. So if I do a line of sight analysis for a specific radar or specific spot, so you can see, guys, you can see here the Earth curvature. You see that white. Let me make it a bit further away. The profile from a spot here to any spot there. You can see the Earth curvature is coming in. So it's not just terrain, and also the Earth curvature. Let me just bring it here. So that white curve here, this is the Earth curvature, the bulge of the Earth, and here is the digital terrain model on the top. Okay, so this is going into the simulations, and for the propagation model. The propagation model here, we take into account the visibility, we take into account the K factor in the computations, 1.33. Okay, and then this is a very simple modeling you can do here. All you have to do is to run the simulation here. Okay, so I'll run the simulation and then we stop this. So this will do the full analysis and then produce for you the calculations. So these are the computations for all the radars and all wind turbines on the map. So let me stop here. And leave room for questions. So John, back to you.
Hello, everyone. Thank you so much for a very detailed briefing, Mr. Yaya. I appreciate that. In order to keep us from getting cut off in the middle of a questions, we have collated all questions and answers, and what we'll do is we'll put those in a document to share with everyone that's been on the call at the end. So there will be a follow-up after this webinar that we will share with all members, that will have all questions and all answers in one document on there. So know that we will get your questions answered, but just in the interest of time for everyone, that we will not be taking any questions live at this time, unfortunately, because we wanted to be sure that we got the demo in for everyone to be able to see that. So Mr. Yaya, thank you so much for that and for taking the time today. So I again, if you do have any questions, you can see there at the bottom of the screen, the contact@atdi.com. You can ask those questions directly. However, we do have all the questions that were put into the chat, and we will put those out to all audience members so everyone can see all questions and all answers after that as a follow-up to this webinar. So we have that, so we will not ask any questions live. I just want to say thank you for taking the time to join us today from around the globe. Thank you to Mr. Yaya Khalid and the ATDI team for making the most of this webinar for everyone, for all of our members and everyone that was able to join us today. I hope this session has given you a clear understanding on assessing the impact of wind farms on aeronautical radar systems. And again, for those that may have further questions or comments, please reach out to contact@atdi.com. Thank you again for your time and engagement, and we look forward to working with you and hearing from you in the future. We will send out this information in roughly about a week after this webinar is over. Thank you so much, and have a great day. I'll turn it back over to the events team.